Hi students, let's discuss now about the directive influence of a functional group in a mono-substituted benzene. If we have a benzene, previously we studied that the most common reaction with the aromatic ring with the benzene is the electrophilic aromatic substitution reaction. That means if you want to do any electrophilic substitution reaction here, the electrophile will replace the hydrogen from the benzene and you get a derivative of the electrophile. This electrophile where you replace the hydrogen by an electrophile. So this is an ES reaction, and this ES reaction on the benzene, this electrophilic aromatic substitution reaction, can occur at any carbon atom, right, in the benzene, because all the positions in a benzene ring are equivalent. So electrophile can attack any of the 6 carbon atoms, right? So all the carbon atoms in the benzene, these are actually equivalent. So in terms of chemical reactivity, every carbon is same. So substitution can occur at any position and you get only one product. There's only one possibility of a product. But if we already have a group attached to it, right? If we already have a ring, a benzene ring, which has some kind of a substitution there, which has a group attached to it. Now the electrophilic substitution can occur selectively. If we have a benzene ring attached with a group, we normally call these two positions as ortho positions, right? This is an ortho position here. This is an ortho position here. And the second, this is the meta position. So there are the two meta positions, two ortho positions, and this one is called the para position. So if you attach a group to the benzene, you got two ortho, two meta, two para. Now electrophile can either attack on the meta position or it can attack on the ortho and the para positions. Depends on who will decide whether the electrophilic substitution now will occur at ortho position or the meta position, at which particular position the electrophile will attack, means what kind of a product you will get. You will get a substitution at the ortho, para or the meta. It is actually decided by the group, right? It is decided by the group. It depends on what kind of a nature the group has. Okay. We normally have two types of groups. We call them as ortho para directing groups and the meta directing groups. So this group over here, it can be an ortho para directing group. Okay, it can be either an ortho para directing group or it can be a meta directing group. That means if the electrophile attacks on the ortho and the para positions, we call this group as the ortho para directing group, and if the electrophile attacks on the meta position, we call this group as a meta directing group, because it is this group that will actually influence, that will direct this electrophile to attack on the benzene ring, right? So we have two types of groups. We have ortho para directing groups and the meta directing groups. In ortho para directing groups, one of the common example is NH2 group, right? If suppose we have an NH2 group attached to the benzene ring, we know in a benzene there is alternate single and double bond, and nitrogen here has a lone pair of electron. Due to the resonance effect, right, at the ortho and the para positions, you will see you get a negative charge, right? Now you will get a negative charge at the ortho position, and then the same charge will delocalize over the para as well, and again at the ortho position, when we draw all the canonical structures. Therefore, obviously the electrophile will attack only at the negatively charged centers here, okay, because it is the NH2 group that increases the electron density at the ortho and the para positions. Hence we say the NH2 group is an ortho para directing group, right? It is an ortho para directing group because it directs the electrophile to attack at the ortho and the para position because it provides electrons. It increases the electron density at the ortho and the para positions. Electrophile is electron deficient, we know that, and therefore it will attack selectively at the ortho and the para position, right? So we have an ortho para directing group. What about the meta directing groups, right? So meta directing groups, one of the group is aldehyde group, right? Suppose we have an aldehyde CHO. This group, when we draw the resonating structures here, we have a double bond, single, then a double bond. Over here the resonance will occur like this. Electron pair will shift in the direction of the oxygen because that is more electronegative atoms, so it will be O negative, H, and we got electron pair shifting in this direction. You got a double bond here, and you got the positive charge at the ortho position. And then again the resonance will occur, it will go to the para position, and again here the resonance will occur, it will go over here. So therefore what we see the positive charge on the ring. Okay, so now electrophile cannot attack on the ortho and the para position because why? Because electron is also electrophile is also electron deficient, right? So electrophile is electron deficient. It won't attack at the ortho and para positions, right? It will only attack now at the meta position because that is the neutral state. So relatively the meta position will be under attack by the electrophile, right? So that is why we see the aldehyde group CHO group is a meta directing group. Okay, this is a meta directing group. So broadly we can say we have two types of groups, right? Ortho and the para directing groups, meta directing groups. Ortho para directing groups, they increase the electron density at the ortho and the para positions, hence electrophile only attacks at the ortho and the para positions. Meta directing groups, they decrease the electron density at the ortho and the para positions, so the electrophile won't attack at these positions, it will only go to the meta position. So therefore it's called as a meta directing group. Okay, let's have some other examples of the ortho and the para directing groups. You can see all these groups that we find here, these are having the electron pairs, right, attached to them. They have the lone pairs NH2, NHR, NO2. It has a lone pair. If you attach any of the group over here, it will increase the electron density at the ortho and the para. So like here also we have OH group, right, hydroxide group, which has got two lone pairs of electrons. So over here the resonance will occur, and what will happen? Okay, in this molecule, the electron pair will be here, it will be over here, positive charge, and again it will increase the negative charge over the para positions here at the para position again, right? When you draw the resonating structures, some other structures, and you get the ortho and the para position negatively charged. Okay, all these groups, any group which has a lone pair of electron attached to it, it will act as a ortho para directing group. Even the halogens, right? Even the halogens can also act as ortho para directing groups, right? Even the halogens can act as ortho para directing groups. Okay, so lone pair of electron undergoes resonance, you get a negative charge at the ortho position. Then another canonical structure, you get over here, then it goes down and it goes up. So that means you get a negative charge at the ortho and the para. So even with the halogens, right, they have lone pair of electron, so electrophile will attack only at the ortho and the para positions. Therefore, what you will get? You will get the product with the ortho and the para substitution, right? So let's take one example here of the ortho para directing groups. Suppose we have a chlorine attached to it, chlorobenzene, and we do any electrophilic substitution reaction. Suppose let's take the substitution reaction of the alkylation, right? Okay, if we do the alkylation here with alkyl Friedel-Crafts alkylation, we have discussed all these reactions previously in the last video. Okay, you can just go back to that and just see the mechanism of the alkylation. Now see, already we have a group attached to it, chlorine, which is ortho-para direction group, which has lone pair of electrons available, and therefore the electrophile, this alkyl group, the electrophile is generated from here is R positive. The mechanism, for the mechanism you can go back to our previous video, and this electrophile will attack at the ortho and the para because the group, the chlorine, is ortho-para direction group. So now you will get a chlorobenzene with the alkyl group attached at the para position, and you will get another product where the electrophile is attached to the ortho position. Correct? So you get the ortho substitute product, you get the para substitute product, you get the two types of products because the group here is ortho-para direction group, and the substitution can occur at either ortho position or at the para position because both are negatively charged. Okay, among the two, the para one is a major product. You can say this is formed in more proportion than the minor, than this one, right? Than the ortho product. This is a minor product. Reason because at the ortho positions, right, the groups are closer, so there is more steric hindrance, okay, and because of the more steric hindrance, it is less stable, right? Here the groups are far away at the para position, so it is more stable molecule, right? This is more stable because of the less steric hindrance between the groups. Okay, electrostatic repulsion here is less, okay, between the groups. Always, if you get the ortho and the para products, you can see most of the reactions, with few exceptions there only, most of the products are actually, the major one is the para one is the major product, the minor one is actually the ortho product. Ortho substitute product is the minor one, and the para substitute product is the major one, because here the less steric hindrance, here the more steric hindrance, here this is the more stable, this is less stable, but there are certain couple of exceptional cases also where ortho is more and the para is major. The reason is different. Okay, so let's take another example of the meta direction groups. As at meta direction groups, they withdraw electrons, right, from the ring. They increase the electron density at the ortho and the para positions. So they decrease the electron density at the ortho and the para positions, right? Like suppose we can talk about the nitro group as well. Okay, we have previously taken the aldehyde group. An example of aldehyde group, it withdraws electrons here. Okay, it withdraws electrons here from the ring. When it undergoes resonance, electron pair shifts in the direction. You get a positive charge at the ortho, and then again at the para, and again at the ortho. So electrophile will not attack at the ortho and the para. It will only go to the meta position only. Correct? Okay. So other examples as well, right? Other examples are also there. These are the electron withdrawing. These are actually the meta direction groups. Suppose we take an example of a benzene. Okay, we take an example of a benzene over here, and then you attach a nitro group to it. Okay, and a nitro group to it. Here this electron pair will shift over here, the pi bond will shift in this direction. You get a positive charge at the ortho, and then the same positive charge resonates at the other ortho at the para positions. So electrophile will only attack at meta position, right? Even you can say the cyanide, right? Also cyanide is also a meta directing group because the cyanide is like this, right? electron pair shifts in this direction, it goes here, and you get the positive charge at the ortho, para and the ortho. So electrophilic substitution will only occur at matter position. So electrophile will only attack at the matter position. So these are the matter directing groups. So any electrophilic substitution that you carry out, that will occur at the matter directing groups. So let's have suppose an example of this one, right? Okay, if you take if we take here an example of a nitro group, okay, if we attach a nitro group to here, and then we do again the suppose the chlorination or whatever it is, right? Okay, any electrophilic substitution reaction we can do, right? Suppose we can do the alkylation also, right? Or you can do the halogenation, whatever it is. Okay, so it will only occur at electrophilic substitution product. It will only occur at the electrophile will only attack at the matter position. So you only get one product here, right? There is no possibility of any other product. So you only get a matter directed product, right? Okay. So one more thing here, what we find that if you have an electrophile, right? If we have an electrophile attacking a ring and already it has a group attached to it, the electrophilic attack may be slow or faster in comparison to the benzene ring, right? So let's take a new topic here. You know, the ring activating and the ring deactivating groups. As I said that if you have a benzene ring and suppose we want to do the electrophilic aromatic substitution reaction, so electrophile can attack at any of the positions in the benzene ring because all the positions are equivalent. But now suppose we have a group, we have a ortho para directing group. Okay, we have a ortho para directing group. Suppose we have NH2 group. Okay, we have an NH2 group attached to benzene. Now as we know that electrophilic aromatic substitution can occur at the ortho and the para position only, because the nitrogen has a lone pair of electron. It increases the electron density at the negative charge, at the ortho and the para positions, and therefore electrophilic substitution reaction will occur at the ortho and the para positions. And the other one is, suppose we have a group which is electron withdrawing group, which is a matter directing group. Okay, and because of its electron withdrawing effect, it will increase the positive charge at the ortho and the para positions. And now if substitution occurs over here, it will only occur at the matter positions. So we have ortho para directing groups, okay, normally, and we have matter directing groups. One more thing in terms of reactivity, if you look at the the attack, if you look at the reactivity of the benzene towards the electrophilic substitution reaction and this molecule, the first one where you have a NH2 group attached, in the first one it will be attack will be faster than the second, than the benzene, right? Electrophilic attack on the aniline here in the first case, in this example, will be faster than the benzene, because benzene, it is a neutral molecule, right? Over here it has a negative charge. Electrophile is positive charge, it is electron deficient, so its attack on the first ring obviously will be faster if we compare it with the benzene. When we compare it with benzene, the attack on the first one in the aniline is faster, right? It will be quick, okay, it will be fast, okay, and that's why we call it as a ring activating group. So we say the NH2 group is basically a ring activating group because it activates the ring to undergo the electrophilic aromatic substitution reaction. So it increases the reactivity of the ring, overall ring, right? So that's why the attack on the first ring is faster than the second one. And then if you look at the nitrobenzene, right, in the third case, in this example, in the nitrobenzene, attack will be slow if we compare it with the benzene, because we have a ring which is positively charged, right? Okay, because we got a ring which is positively charged here. Okay, this is a positively charged overall ring, so its attack on the electrophile, attack of the electrophile on the positively charged ring will be relatively, it will be slow with in comparison to the second, in comparison to the benzene. So overall order of reactivity, we can say that NH2 group is faster than benzene, and benzene attack of the electrophilic aromatic substitution reaction will be faster in benzene than the nitrobenzene, this one. Correct. So we have basically, we categorize those groups again into ring activating groups as well as in ring deactivating groups, right? So ring activating group is the one which can increase the electron density at the ring, and therefore the attack of electrophile will be faster. Ring deactivating is the one which decreases the electron density at the ring, so therefore the attack will be slower. Okay, so in terms of reactivity, we can say the electrophilic aromatic substitution reaction will be faster at aniline than benzene than nitrobenzene.